Hello. In today's lab, we will use the resonance of air columns to measure the speed of sound in air. In the last lab, we used the resonance of the transverse vibrations of a string. When the string resonated with the tuning fork, we set the fundamental frequency of the string equal to the frequency of the tuning fork. In the same way, in today's lesson or in the lab, we will set a column of air inside a tube to resonate with the frequency of a tuning fork. Well, when air enclosed in a closed tube resonates in its fundamental mode, this will be the mode of vibration. I'm sure you have seen this in the theory class. There will be an antinode at the open end, a node at the closed end. Now, if you remember, in a stationary wave, the wavelength is the length of two complete segments. In other words, the distance between two alternate nodes is a full wavelength. Therefore, if you look inside the closed tube for the fundamental mode of vibration, the length of the tube contains the distance between an antinode and a node. Tell me, if one full wavelength is the distance between two alternate nodes, what will be the distance between a node and an antinode? It is a quarter of a wavelength. So we can say the length L1, in this case, we got to say L1, the length of the tube is actually a quarter of a wavelength. But you need to apply a small correction there. And what is that correction? The correction is the antinode generally occurs slightly above the mouth of the tube. Now here I have marked that as X. That means a quarter lambda occurs at a distance L1 plus X. The length of the tube is L1. And so we can therefore say this L1 plus X will be a quarter lambda. I'm going to write it out here. L1 plus X equal to a quarter of the wavelength. Now, in the next mode of vibration, suppose the length of the tube is L2. If you now increase the length of the tube, the same tuning fork will resonate with this air column when it is vibrating in the second mode. Now tell me, what is, if the length of the tube now is L2, that is, this length is L2, then L2 plus X, look at that, this is the antinode there, L2 plus X will be what part of a wavelength? This is a quarter wavelength, this is a quarter wavelength, this is a quarter wavelength. We can say L2 plus X equal to 3 lambda divided by 4. Now, this is the theoretical background we are going to use. In fact, let me show you the equipment that we will be using. I think I need to zoom out to make it clear. Alright, give me a second. Here I have a glass tube. The glass tube is open at the top, and this is the top side of the tube. The tube encloses a column of air. There is the column of air. And I can increase the length of the column of air. You can see I have some colored water there. I can increase the column. Now watch how the length of the air column can be increased. I can let the water fall, and I can increase the length of the air column, or I can decrease it. You can increase or decrease by varying the position of this reservoir. You can see if I raise it up, the column will begin to rise and the length of the air column will decrease. So I can actually change the length of the air column by allowing the water to flow in or out of the tube. So in the experiment, what I will do is I will vibrate a tuning fork and keep it at the mouth of this tube. You may not be able to see it, but I will keep it at the mouth of the tube, and if the frequency of the air is equal to the frequency of the tuning fork, then you will hear a loud sound. Now when you hear a loud sound, you should know the column of air is resonating with the frequency of the tuning fork. Now when you hear the first resonance, this will be the mode of resonance. That is for the first resonance. Now after the first resonance, I will allow the water to fall again until I hear a second resonance. Well, when the second resonance occurs, this will be the situation. So for the first resonance, L1 plus x equal to lambda by 4. Now what does this x stand for? This x is the small distance above the top of above the mouth of the tube where the antinode is formed. Actually this is called the end correction, and I want you to determine the value of that end correction. Okay, so L1 plus x equal to lambda by 4, that is the equation when you hear the first resonance. And for the second resonance, the equation is L2 plus x equal to 3 lambda by 4. Must be L2 plus x. And now, you can eliminate x from these two equations if I name these two equations as equations 1 and 2. Let me do that. If this equation is equation 1 and this is equation 2, what do you get if you subtract equation 1 from equation 2? Well, I'm going to subtract equation 1 from equation 2. On the left side, I get L2 minus L1. Is that right? L2 minus L1 plus x minus x is 0. And on the right side, I get 3 lambda by 4 minus lambda by 4. What is 3 lambda by 4 minus lambda by 4? It is 2 lambda by 4, which will be lambda by 2. So, we get L2 minus L1 equal to lambda by 2, or I can say lambda equal to 2 times L2 minus L1. And we are using this experiment to measure the speed of sound in air. If V is the speed of sound, we have V equal to F lambda. Now, lambda is 2 times L2 minus L1. Therefore, I can write V equal to F times lambda. In place of lambda, I will write this. So that will be F times 2 times V2 L2 minus L1. Is that right? Yes. Now, this is the equation for our lab. Tell me, what are the variables in this equation? I have been asking you, every lab you have an equation, and you need to write that equation in the form y equal to mx. Alright, I'm going to do this for you. In the last one I did not do it. I don't know whether you did that in the right way. But let me show you this one more time, how to do that. What are the variables in here? This will be L2 minus L1. Now, this L2 minus L1 will vary when the frequency varies. So, frequency is a variable, L2 minus L1 is another variable. So, in the experiment, we will do the experiment for different tuning forks. I have, I think, 2, 4, 7 tuning forks. We will do it for 7 tuning forks. And each time you change the frequency, L2 minus L1 will change. So F is the independent variable, L2 minus L1 is the dependent variable. That means you solve for the dependent variable. In order to write your equation in the form y equal to mx, always solve for the dependent variable. And solving here for the dependent variable gives me L2 minus L1 equal to V divided by 2F. Is that right? V divided by 2F. Now, when you write that in the form y equal to mx, knowing that L2 minus L1 is a variable and F is another variable. So how do you write it in the form y equal to mx? Look at the way I write it. I say L2 minus L1 equal to V over 2 times 1 over F. Now, this is the dependent variable, that is your y, and this is the independent variable, and that is your x. So, you now draw a graph of 1 over the frequency, 1 over f on the x-axis, and L2 minus L1 on the y-axis. The slope will be V over 2. And using the value of the slope, you can calculate the velocity of sound. Alright, that is the way we write the equations in the form y equal to mx, and how we use the slope to determine the quantity that we want to measure. Experiment, I will set a tuning fork into vibration and hold it at the mouth of the tube and allow the water level to fall. Now, when you hear the loudest sound, you've got to be very careful listening to it. When the sound is the loudest, you stop the video and measure the length L1. Now, where is the length measured from? From the top of this black holder, there you are, to the surface of the water. That is your L1. Now, after measuring L1, continue the video. I will allow the water to fall further and you will hear a second loud sound. Now, stop the video there and measure the length L2. So you have, for each frequency, you will have a length L1 and a length L2. And that will be repeated for 7 different tuning forks. And also, I have a tuning fork whose frequency I don't know. It is not written on this. I will set this into vibration and hold it on the mouth. You measure L1 and L2. And at the end of the experiment, when you draw a graph, we have talked about what kind of graph you're going to draw. Use your graph to figure out the frequency of this using the lengths L1 and L2. Alright, we're going to start with the first tuning fork. Alright? Since you will be taking measurements on the computer screen, we will start by obtaining the conversion factor. Now here I have the 30 centimeter ruler. Measure the length of this on the computer screen. Alright, and record your measured length as X. And calculate the conversion factor how do you calculate the conversion factor? See the conversion factor equal to 30 centimeter divided by your measured X centimeter, and record this conversion factor. Every time you make a measurement on the computer screen, you multiply that with the conversion factor. Okay? As I said to you earlier, I will run the water continuously, and when you hear the first loud sound, stop the video. Now remember, you can go back and forth to get that exact spot where the sound is the loudest. Measure L1 and then stop the video again when you hear the second loudest sound. Measure the length L2. The first frequency I'm going to use is 329.6 Hertz. Alright, measure L1, measure L2 and complete your tables. Alright, let's go. I'm going to run the water. Alright, the water is falling now, and I'm going to vibrate the tuning fork and hold it at the mouth. Well, it takes patience, so listen to it very carefully. See, the first loud sound is over. Hear the second loud sound? Yes. There you are. Now you must take 2 measurements each for L1 and L2. Now take the video back and forth and do the experiment again. So take 2 measurements for L1, take the average, 2 measurements for L2 and take the average. Alright, now we will repeat the experiment using a frequency of 349.2 Hertz. Alright, I will again keep the water up to here and run it continuously. You need to stop when you hear the first loud sound and then the second loud sound, and each measurement you take twice and take the average. Alright, let's now take the measurement for the frequency 349.2 Hertz, and let me run the water. And listen for the loud sound. There you are. And now look for the second resonance, for the second loud sound. I'm sure you got the second resonance. If you think you were fooled by some stray loud sound, you need to go back and repeat it. Alright, so try and get the best results for the first loud sound and the second loud sound. Okay, we will now repeat the experiment for a frequency of 392 Hertz. Alright, listen carefully for the first loud sound. Let me let the water flow. There, it's flowing. Okay. I'm sure you got the first resonance. We will now look for the second resonance. Got to have patience. That was not the loudest sound. Well, by now you have an idea of how the loud sound actually sound like. Alright, so here distinctly you have the first and the second resonance. Okay, we will now repeat it for the next tuning fork, that is 440 Hertz. Okay, 440 Hertz, and now listen for the loud sound for L1. A beautiful resonance. Okay, let's now look for the second resonance. I'm going to let the water out a little faster. So the second resonance is passed. Our next frequency is 494 Hertz, and let's look for the resonances, the resonant lengths of L1 and L2. Alright, watch carefully, listen carefully, alright? Well, the resonance is passed. Look for the second resonance. Let out the water a little faster. Alright, you've got to be careful here. Stop when you hear the loud sound. the second resonance is passed. We will now repeat the method for a frequency of 512 Hertz. Okay, let me run the water and listen for the loud sound. Loud sound is passed. Okay, we will now look for the second resonance. I'm going to let the water flow a little faster and listen to it carefully. There, the second resonance is passed. We will now repeat the procedure for a frequency of 523.2 Hertz, and let me run the water and get ready for your measurement. All right. Yes. We will now look for the second resonance. I'm going to run it a little faster. Okay. Yes, the second resonance is passed also. I have now the tuning fork of unknown frequency. Measure your length L1 for the first resonance, L2 for the second resonance, and figure out that unknown frequency. Alright, let me run the water first and listen for the first resonance. The first resonance is passed. Let's now go for the second resonance. the second resonance is passed also. As I said to you earlier, fast forward and rewind the video several times so that you have the best result when you hear the loudest sound. And take at least 2 measurements. In your tabulation, I want to see both those values. Reading 1, reading 2, average. Similarly, reading 1, reading 2, average. Okay? And continue with the recording of your result and tabulate them neatly, draw your graph, obtain the velocity of sound from your experiment, and also obtain the frequency of the tuning fork, which we are not sure of the frequency. Okay, I will see you for the next lab later on. If you have any questions about this, let me know and we will discuss.